Our learning goals for today are to talk about what a multi-stage event is, and then we're going to learn how we can use tables to help us describe a multi-stage event and work out probabilities for multi-stage events. And if we get time, I might save this to the next video, but if we get time we'll have a look at the difference that replacement makes to the probability of an event. So we'll talk about that in a little while. So let's start though with what is a multi-stage event. Okay, well, like the name suggests, multi-stage events are events that have more than one component or stage to them. Sometimes we call them compound events, sometimes we call them multi-stage experiments, sometimes we call them multiple events. And a good way to clarify what I mean by this is to look at a couple of examples. If I toss 2 coins, it becomes a multi-stage event. The first stage is the results of the first coin, and the second stage is the results of the second coin. You might still toss them both at exactly the same time, but it's still a multi-stage event because there's 2 sets of outcomes, a set of outcomes for one coin and a set of outcomes for another coin. Maybe tossing a coin and then tossing a die. So you can see that they have 2 distinct stages. It can make it difficult then to keep track of what's going on in a multi-stage experiment because there's this combination of possible outcomes. So I'm going to show you today how to use a table to keep track of multi-stage events. I should note also that when you're listing the outcomes of a multi-stage event, order is important. So, for example, if I go back to that example of tossing 2 coins, I would note that the outcome heads for the first toss and tails for the second toss would be a different event than tails for the first and heads for the second. And I'll show you what I mean because we're going to do that as an example. Let's have a look. So here we are, we've got our multi-stage experiment is tossing 2 coins. So you can see here on the table that I've got as my columns, I have the results of the first toss. So for the first toss I could get a head or a tail, and then as the rows I have the results of the second toss, a head or a tail. So let's have a look at that. What that gives us. It gives us 4 possible outcomes. I can get a head and then a head denoted by HH here. I could get a tail for the first and then a H for the second. I could get a H for the second, for the first, and a tail for the second, or I could get a tail for both tosses. So if I wanted to list the sample space of this multi-stage experiment of tossing 2 coins, it would look something like this. There's my symbol for sample space, and there's my curly bracket to open up my sample space. I would have HH, tail H, HT, and TT. A bit squishy there. So the thing to notice is because we've said that the order is important, it means that these count as 2 different possible outcomes. So that means that the number of things in my sample space is actually 4. That outcome, that outcome, that outcome, and that outcome. So you can see how it could get confusing. If you counted those 2 as the same thing, you would only have 3 outcomes. But order is important, so it has 4 outcomes. Okay, let's use this handy table to work out probability. our first probability question is, what would be the probability of getting a head first and then a tail? So the outcomes that I'm interested in are only this one outcome, head then tail. So the probability of head then tail would be equal to the number of outcomes that give me what I'm interested in, which is only 1, over the number of possible outcomes from the experiment, which we've worked out as being 4. So the probability of getting head first then a tail is 1 on 4, or 0.25. That's just the decimal conversion, or 25%. Okay, here's another question. What is the probability that you would get at least one H? Okay, so first of all, let's call that A. So the event A is the event at least one H. So we want to know what is in the event space of A. So at least one H means that this is in it, because that has 2 H's. This has 1 H, so that's in it. This has 1 H, so HT is in my event space, but this doesn't have 1 H. So I have 3 possible outcomes in my event. So we'd say the probability of A is equal to the number of outcomes in my event, which is 3, divided by the number of outcomes in my sample space up here, which is 4. So the probability of tossing 2 coins and getting at least 1 H is 3 over 4, or 0.75, or 75%. Okay, good idea to do some examples now to solidify that for you. So if you're watching this video, I'm going to ask you to go and do some questions in 9D. Okay, I'm back. I want you to stop the video now and go and do question 1 of 9D in your textbooks, but I'm going to keep going. Let's have a look now at this idea of with replacement and without replacement. So if I'm choosing something, I'm choosing lollies from a bag, for example. If I'm choosing lollies from a bag, I can work out the probability of getting a Sherby by counting the number of Sherbies that are in the bag, and then counting the number of lollies in total that are in the bag, and dividing the number of Sherbies on top by the total number of lollies on the bottom. But say I take a Sherby out and I eat it. The probability of getting a Sherby the next time is going to be different, because there's now 1 less Sherby and, of course, 1 less lolly in the bag. So probabilities change depending on whether you are going to replace the thing that you choose. So let's have a look at example. We've got 3 letters, the letters from the word cat. So C, A and T, and we're going to choose 2 letters from the word cat. So this is a multi-stage event because I'm choosing two letters. So I've set up my table with the columns representing the first choice and the rows representing the second choice. And notice that the C and the A and the T are present in the first choice, but they're also, C, A and T could also be chosen the second time. I'm just going to get rid of all my scribble because it's annoying me. Okay, so we choose a C the first time, and then we have our second choice. Because we're going to replace the C, this is the example with replacement, it's possible for me then to choose C again. So I could get an outcome here of C, C. So I choose C in the first time, I may then choose A the second time, I may choose T the second time. So I get these three outcomes and they're dependent on the first choice of C. Say the first choice I've chosen A. Well, I can then choose a C, or I can choose another A because I have replaced the A. This is with replacement. Or I could choose a T, and so on. So you can see from this table here that I have 9 outcomes when I am replacing the letter that I choose after my first choice. Let's have a look at what happens if we don't replace it. So this is without replacement here. If I choose C in my first choice, then C is no longer available for my second choice. So it's not possible for me to have that outcome C, C. I can choose A for my second choice and T for my second choice, but I can't choose C again. If I choose A for my first choice, then A is no longer available for my second choice. So again, I have 2 possible outcomes. I could choose an A and a C, and an A and a T. For T, I can choose a T and a C, and a T and an A, but I can't choose a T and a T, because on the first choice, that T was removed. So now I have 6 possible outcomes when I do not replace the choice of the first pick. So you can see then that if I want to calculate probabilities, I need to know whether or not replacement is occurring, because in this example here, my probability of, say, an event A, don't worry too much about what A is, would count the number of things in A, and I would divide it by the number of things in my sample space. And in this case here, that's going to be NA over 9. But in this case here, the probability of A, whatever A is, would be the number of events in A divided by 6, because there's only 6 possible outcomes. Let's do an example together. 2 letters are chosen from the word tree without replacement. List the outcomes in a table. Okay, so let's do this. Choice 1 will be our columns, and choice 2 will be our rows. So in choice 1, I have T, R, E, and E that can be chosen. And for choice 2, again, T, R, E, and E. It's not as neat when I do it, is it? Alright, so let's divide that up and work out what our possibilities are. I'll use another pen. Okay, so say I choose T the first time, and it is without replacement. So if I choose T the first time, T is not available the the second time. If I choose T the first time, R is available, so I could get TR. E is available, I could get TE, and a different E is available, so I could get TE again. Let's have a look at if I choose R the first time. Well, I can then choose T, but I cannot choose R. Actually, rub these out together. I cannot choose R because R is gone and I'm not replacing it. So I can choose E, RE, and RE. Always choose RE. RE is good for you. Let's say in choice 1 I choose E. Well, I can get a T. I can get an R. I can't get the same E, so that one's gone. But I can get this other E. Aha! Complicated. And you're noticing the pattern. The ones that are disappearing are the ones on the diagonal here. So I could get ET, ER. I could get this E and that E, but I can't get that E and that E. So how many outcomes do I have? What is the number of outcomes in my sample space? That's what this means. The number of outcomes in my sample space is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I need to know that for my probability calculations. Let's have a look at the B section of this question. Let's tidy up a little bit. B says, find the probability that the two letters chosen are both E. Okay, so we need to find out how many times both E happens and then divide it by the number of outcomes in my sample space. So I already know that I'm dividing by 12. So let's go and count the both E's. How many times does that happen? It happens there and it happens there. So the probability that I'll get both E's is 2 on 12 or 1 on 6. Simplifying that fraction. Alright, let's look at C. What is the probability that at least 1 is an E? Okay, let's, it might make it clearer if we write down the event space. So we want to write down all of the events that are part of at least 1 is an E. So these are curly brackets. RT doesn't fit because there's no E's in there. ET fits. ET again. Go to the next row. TR has no E. ER does. So remember it has to have one E or more than one E. So there's another ER that also fits. TE fits. RE and EE from row 3. Quite a few things in here. Then in row 4, TE, RE and EE. TE, RE and EE. So that's a lot of stuff in that event space, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of at least 1 E would be equal to the number of events that we've outlined here, which is 10, divided by the number of events in our sample space, which is 12. So 10 over 12, 5/6. So I'll get you to do all the even-numbered questions in exercise 9D. But as I said to many of your parents who came to attend to you, you are always welcome to do more if you want to. Okay, thanks girls, have fun.